All right, so this is 6.70, and we're looking at Nadine and figure skating. In your calculator, go ahead and enter in this equation. Negative x squared, oops. Clear, y equals negative x squared plus 6x plus 1. And this is her velocity. The velocity is measured in meters per second. We're going to look at the graph of that one. We'll look at the table as well. Question 1 says to describe her velocity over this 5-second interval. This is her velocity over a 5-second interval. If I go into graph, let's see what my window looks like. I'm going to need to change that. So window, x min 0, x max 5. And then as far as the y values go, I'll go 0 to 10. Let's see if this shows up. That's a pretty good graph. So over the 5 seconds, the y value on this graph represents her velocity. So from 0 to 1 second, what would you say about her velocity? It's increasing. How about 0 to 2 seconds? Also increasing. It looks like at 3 is when the velocity gets its maximum. This is a parabola, so I have a nice little formula, negative b over 2a, where I can calculate that. I could also go to second table. Go to table set. Start at 0, and I'm going to make it to be auto instead of ask. So back to the table. So my velocity at 0 seconds, 1, 2, at 3 seconds, then it starts going down. I can see the nice symmetry with these. So at t equals 3, we get our maximum velocity. What would the label of that be? Velocity is in meters per second. So question 1, describe Nadine's velocity over the 5-second interval. Turn to your friend. Can you describe that? Go. Colin.
We're going to do x equals what? X equals s? Sure. Why is it going down? I think I did this wrong.
So I could say that her velocity increases for the first 3 seconds, then her velocity starts to decrease. What about speeding up versus slowing down? Is she speeding up for the first 3 seconds? The velocity is positive because these y values are positive. What would you say about the acceleration? It's positive because that's the derivative of velocity is acceleration. So the tangent line would have a positive slope. So she's speeding up for the first 3 seconds. And then after 3 seconds, her velocity is still positive. How do we know she's slowing down? Because velocity is positive and acceleration is negative. So describe her velocity over the 5-second interval. I could say her velocity is increasing for the first 3 seconds and it's decreasing for the final 2 seconds. Number 2, interpret the integral of 2 to 5 v of t dt in the context of this problem. So giving myself a little graph over here. There's 5, 2 was somewhere about right there. The horizontal axis is time in seconds. The vertical axis is the velocity in meters per second. And so far, when we see that integral symbol, we're thinking about it as an accumulator. It's accumulating all of the area under the curve. So if I find the area under the curve from 2 to 5, what would that unit be? Meters. So talk to your friend using numbers 2 and 5, using the labels and so forth. Can you describe what this means? Go.
How far they gone in between, or say in 3 seconds? So like after the second for 3 seconds.
All right, let's talk about the numbers 2 and 5. What does that represent? Starting and ending in seconds, that's the dt. Whatever this d, whatever is at the end, what you're integrating with respect to, that'll give you the label on your upper and lower bound. So from 2 to 5 seconds, Nadine's, the label here is going to be meters. So what does that meters represent? Her displacement. What does displacement mean? Her change in position. In meters. And because everything is positive, it would also be the distance traveled for this one. Once you start getting into negative velocities, that's when displacement is going to be a bigger deal about your change in position. What's the difference between distance traveled and displacement? If I am starting right here and take 2 steps to the right and 1 step back, that would be a distance traveled of 3 steps. But my displacement is only 1 step because I'm 1 step different from where I started. This is a displacement that we're talking about here. It's the change in position in meters. Question 2 says, evaluate this integral using Math 9 on your calculator. Okay, so back to my calculator. I'll go back to the regular screen. And Math 9 is the integral symbol. So we're doing the integral from 2 to 5. And I don't want to have to type in that whole equation again. It's already in y1. Oops, I have 55 up there. Delete. There we go. I don't have it yet. All right, so I'm going to put y1, and I'm going to go vars for variables to the right, y variables, choose the function. And I want to grab y1. Since I've already put it in there, I'm not going to type it all over again. I'm just going to grab the function y1. I want to find the integral from 2 to 5 of the function y1 with respect to x. So this is going to evaluate that area under the curve. It's going to accumulate those infinite number of ultra-fine rectangles in there, and it's telling me that that area is 27. The other way I can do it is looking at the graph. If I go here, I can go second calculate. This time it's option 7. It's still that integral symbol. So I'll choose option 7. The lower limit I want to be 2. The upper limit I'm going to have 5. And then it nicely shades in that color for us. It's saying this is the area that we're actually finding. And at the end it says that area is 27. So this gives us a visual. On the regular screen, you can see I went a lot faster. But to the context of the problem, the integral from 2 to 5 v of t dt is 27. And what did we say that label was? Meters. So from 2 to 5 seconds, Nadine traveled 27 meters. That's what we get by accumulating the area under the curve, which again has a label of meters on it. All right, question 3. Give a possible position function s of t that could represent Nadine's position in meters from one end of the rink at time t. Now, some things we have to recall. Velocity is velocity, right? How does velocity relate to position? If I have a position function, what do I do with this to get to its velocity? The derivative. So S prime of t would be equal to V of t. So as I'm thinking about this one, to get the position, I want to know what function that when I take the derivative of it gives us this velocity equation. We're going backwards. We've used this term integral quite a bit. We're finding the integral of this. Another way you hear it phrased is the antiderivative. Anti means the opposite, other direction. Instead of finding the derivative of V of t, we're going to find its the derivative. So in other words, what function, if I took the derivative of it, would give us V of t? I'm thinking backwards to get this one. Okay, so point by point, or piece by piece. S of t equals the derivative of what would give us negative x squared. Think power rule. The derivative of what is negative x squared? Negative 1/3. A little bit more. X to the 3. Is the derivative of this equal to negative x squared? Yeah. And then the derivative of what would give us 6x? The derivative of what would give us 6x? 3x squared. The derivative of this is your 6x plus the derivative of what is equal to 1? X. And then the position is this. What if I added a number at the end like plus 7? If I took the derivative of this S of t equation, if I took the derivative of this, does it give us to that velocity? Piece by piece by piece. What's the derivative of 7? 0. So I could really add any number at the end, right? So there is our position function. Question 4 then says, using this equation, find the change in position between t equals 2 and t equals 5. We really already did that. We used our calculator. We said that this integral represented that change in position. Now we have a possible position function. The plus 7, again, I'm not really sure about. It could be that. It could be something else. We're going to find the change in position using this. In other words, let's do some calculating. Calculate S of 2. So I'm plugging 2 in. That's negative 1/3 times 2 cubed plus 3 times 2 squared plus 2 plus 7. I'm going to simplify that just a little bit. Some of it just looks kind of messy. I'm going to deal with the numbers at the end first. 2 squared is 4. 4 times 3 is 12. 12 plus 2 is 14. 14 plus 7 is 21. Out front, 2 cubed is 8. 8 times negative 1/3 is negative 8/3. So here's one way to talk about S of 2. And I'll simplify it just a little bit more. To get a common denominator, wouldn't that make this 63 over 3? So 63 over 3 minus 8 over 3, isn't that 55 over 3? What did I just do right here? Well, at 2 seconds, Nadine's position relative to like an origin, a starting point, is 55/3 meters to the right. So at 2 seconds, that's where she's at. S of 5. Not here today. Sorry. S of 5. So now plug 5 into that potential position function. Negative 1/3 times 5 cubed, 3 times 5 squared, plus 5 plus 7. I'll deal with the numbers first again. 5 squared is 25. 25 times 3 is 75. 75 plus 5 is 80. 80 plus 7 is 87. 5 cubed is 125 times negative 3. That's negative 125 over 3. I'm going to use my calculator. 87 minus 125 over 3. Math frack. 136 over 3. So because the velocity was positive, right, from my original graph that we looked at, because my velocity was positive this whole time, even though Nadine's slowing down, her velocity was still positive, so she was moving in the positive or the right direction. That's why this position is further to the right. So at 5 seconds, she's at 136/3. What is her change in position? What are you going to do with those two numbers? Subtract them. Take S sub 5 minus S sub 2. 136/3 minus 55/3. And what does that come out to? 27. Remember, I totally guessed up here with that +7. Does that mean I got the right thing? No. The +7 was added to one. It was added to the other when we ended up subtracting them. When I took this S sub 5 minus that S sub 2, I could have just as easily said, well, go ahead and subtract the like parts. Take this minus this. 5 minus 2 is 3. Subtract those, subtract those. That +7 didn't matter. But what's significant, question number 5, how are your answers in questions 2 and 4 related? Well, in question 4, when I found this antiderivative and plugged in the position at 5 minus the position of 2, that was the same thing as just going straight for that integral function on the calculator. So how are they related? They're the same. And that's going to be a pretty significant thing for us. We've talked about this integral symbol being an accumulator of area. It has another connection to it as well, and it deals with this idea of an antiderivative. Question 6. At t equals 2, Nadine is 12 meters from the edge of the rink. Remember, in question 4, with the equation I had, this +7, I had her being 55/3 away from the edge of the rink, from position at 0. They're saying actually when t equals 2, Nadine is 12 meters from the edge of the rink. So let's take this S of t equation. S of t equals -1/3, should be t cubed, not x, plus 3t squared plus t plus, I put +7. What notation could we put at the end to stand for her initial position? We could put x, any variable we wanted to. Now, can you run that through? How do you plug the 2 and the 12 into this equation to find the value for x? Where does the 12 go? S of t, that's their actual position. Where does the 2 go? All the t's. -1/3 times 2 cubed plus 3 times t squared plus t plus x. The goal here is to solve for that x. So you're taking 12 plus 8/3 to get it off of the right, minus this 12 to get that off of the right, minus 2, that'll give us our value for x. So 12 minus 12, 8/3 minus 2, that's 8/3 minus 6/3, so x is equal to 2/3. So what did I just find for this one? Well, her actual position is -1/3 t cubed plus 3t squared plus t plus 2/3. I haven't answered question 6 yet, and I'm going to pause for a second. So either using this equation or using other information in logic, can you go back and answer question number 6, which asks, where is she at t equals 5? Go for it.
and then just plugged in 5. Put in 5 and then put in 2/3 as x, and I got 30.
All right, here we go. 2 ways. Let me explain probably the more involved way and probably the harder way. Since this is the actual position function, and I know that because if I plug 2 in for t, it gives me a position of 12, which is what we're told is true. So then if I plug 5 in for this, run it through the equation, that should give me her actual position at t equals 5 seconds. That would be true. There is a quicker way, though. If Nadine at 2 seconds is at 12 meters, then where is she at 5 meters? Remember earlier we said that her change in position, her displacement was 27 meters. So if she was here at t equals 12, where should she be at 5 seconds? (39). Add 27 to that. So she should be at 39 meters from the edge of the rink. So either way, we should get that same answer. So again, there's this strong connection between the change in position and the integral. Go ahead and turn the page. Notation time. Integral from a to b of f of x dx is equal to, so when you see an integral like this, you're really thinking through 2 things. If this was a graph, what is the accumulated area under the curve from x equals a to x equals b? But I'm also thinking in the world of antiderivatives because I don't want to always rely on my calculator to do this for me. And I don't always have great area formulas that I can use because not everything is going to be nice and linear. We're going to have random curves. So this integral can be defined as capital F of x from a to b, which we'd evaluate as f of b minus f of a. What do you think is the relationship between lowercase f and capital F?
Well, I just have a question. Is that a lowercase f?
So what do you think of the relationship between capital F and lowercase f? Where capital F prime of x is equal to lowercase f of x. Capital F is called the antiderivative or integral of the original. And you're going to see that notation quite a bit. Where when you integrate something, a lot of times we change it from a lowercase letter to a capital letter. It's not always a given that that's what it means, but that's kind of what's implied in some of them. And I have to make sure I'm explicit and say that one. So if you actually find the antiderivative of that, take the upper bound minus the lower bound, that will give you your change in position, your displacement. Other equation, other notation. And this one is going to be very significant for us. It looks like it's a lot, but it's just building off of what we had on the first page. And you probably don't recognize it this way yet, but this equation I wrote down here is, ready for it? It is point slope form. What is point slope form? Y minus y1 equals slope times x minus x1. That's essentially what this is. Now, it doesn't look exactly like it because from this point slope form, a few things were done. One thing was to add y1 to both sides. So y equals y1 plus m times x minus x1. This is essentially what's going on right there. This y1 value that I have is an initial value. It's something that I know, and that's the same thing as this capital F of A. We call this our initial value. From the previous page with the skating example, we were told that at 2 seconds, her position was 12 meters. That's what we knew to begin with. This is the accumulated change, the displacement. How far did Nadine move in her skating example? And that's kind of what this is all dealing with as well. It's the change in position. The slope times x minus x of 1, it is the change in position. So if we have an initial value, I told you where you started, and I told you what you changed by, then what do you think this is going to represent? The final value. It's where you're ending at. So again, it might look like there's a lot going on here, and there really is, but it's just like a point slope where we have an initial value plus the accumulated change gets you to a final value. Sometimes when you see it in notation, it looks a little confusing, so let's see if we can apply this. Question 1, the temperature of water in a tub is given by strictly increasing twice differentiable function W of T. So a little bit going on with that, strictly increasing, which means that the WT values need to keep going up over time. I don't have a lot of values in here. There's a lot of gaps between the time and minutes, but at no point does the temperature actually ever go down. It's a twice differentiable function, which means it's very well behaved. There's no holes in the gaps. It is continuous. It is differentiable. There's no sharp turns. We like it when that happens. Selected values of W of T are given in the table below, and now we're asked to evaluate this. Now, I could graph all this and get a visual of what's going on. And maybe that helps with as far as like what the label is going to be. In here, it says W prime of T. W of T is degrees Fahrenheit. What would be the label on W prime of T then? W prime with respect to T. So what would be the label on W prime of T? Degrees per minute, right? With respect to T, with respect to time. So whatever the graph looks like, it is increasing. The vertical label is in degrees per minute. My horizontal is dt in terms of minutes. So if I find the area under the curve from 0 to 20, find all that area as curved as it might be or as linear as it might be, what would be the label on this region? Degrees. So when we're evaluating this integral, the label is going to be degrees. That helps me out a lot in these various problems. So integrating this. The integral of W prime, that's the antiderivative. That's taking it up a level, right? It's going from velocity to position. What would be the integral, the antiderivative of W prime? So when I ask that question, I'm saying like the derivative of what is W prime? W. So the integral of this is W of T. And we have these definite bounds going from 0 to 20. All right, so I'm using a little bit of this notation that from up above. I didn't have to go capital because the W prime in here, when we integrated that, I was able to get rid of the derivative. So the derivative of W is W prime. I feel good about that. Now we're supposed to take W of 20 minus W of 0. Do we know those values? W of 20 says it's 71.0 minus W of 0 is 55.0. So subtract those and we get 16. Here's where I'm going to pause for a second and have you talk through this one. There's the value of 16. Interpret your answer in the context of this problem. So talk about the 0, talk about the 20, talk about the 16. Make sure you're using labels and appropriate terms. Go for it.
how much degrees change between 0 and 20 degrees.
Join. Oh, no, I don't know.
Okay. What do the 0 and 20 stand for? What's the label on those? Minutes. So from t equals 0 to t equals 20 minutes, I'm interpreting. There's my interpretation of the 0 and the 20. What does W represent? Just the variable W of t, what does it represent? The label is in degrees. What does it represent? The water temperature. The temperature of the water is 16. No, the temperature of the water changes. Could we say increases? It's positive. If it was negative, we could have said decreases. Either changes or increases by 16. What's the label? Degrees Fahrenheit. There is the interpretation. So there was a table example. Now we have a graphing example. It says the graph of g prime of x is given below. If g of -2 equals -11, find g of 4. Find g of 4. Let me help you in getting this one set up. G of 4 equals, do we know an initial position? Yeah. So I could say g of -2. More specifically, I could put a -11 in there. G of 4 is equal to what I know where the particle, wherever the point is at g of -2, plus the accumulated change going from what lower bound to what upper bound? -2 to 4. The x values are changing from -2 to 4. How were those values chosen? Well, they were chosen because my computer's running a little slow. Let's just rewrite that. They were chosen because I know where we're starting at. I know the y value at x equals -2, and I want to find it when x equals 4. The accumulated change of the derivative dx. So g of 4 is equal to g of -2 where it is at, plus the change. That's why we have the derivative, the accumulated change from -2 to 4. I can plug some more numbers in here. We want g of 4. G of 4 equals, what is g of -2? -11, that's where it's starting at, plus this in total change in the position. So from -2 to +4, we're supposed to find that area under the curve. Let's talk about this region first. What kind of shape is that? Semicircle. The area of a circle is pi r squared. The area of that semicircle is 1/2 pi times what's the radius squared? What's the radius? 2. So 2 squared. And if we evaluate all that, what does this come out to? 2 pi. So again, I could do g of 4 minus g of -2. I don't know what the function g really is, but I can find the accumulated change under the curve. I can find the area under the curve. So this part of it is 2 pi plus, what is this area? What is the integral under this derivative? 1/2 base times height, so 2. So here is what g of 4 is equal to. If you wanted to, you could simplify it a little bit. If it's multiple choice, it would probably say -9 plus 2 pi. However, the green above it is just good enough for free response. That is where that is what the G of 4 value is going to be. Where it started plus the accumulated, that's the integral, the accumulated change. The change is a derivative part. All right, read number 3.
So what is G of 8? So isn't G of 8 is equal to 5 plus, I'm saying D, my answer, final answer, D.
When it says G is the antiderivative of F, that means if I had G and I took its derivative, that should get us to F. That's what that blue part means. If I integrated F, it would take me up to G. If I took the derivative of G, it'd take me back to F. All right, turn to your friend. Which one of these is going to give you the value for G of 8? Which one are you most convinced is wrong? Not even anywhere near it. B, C, and D, they all have integral from 3 to 8. Does that make sense why it is? We're changed from 3 to 8. I'll tell you C is wrong. What does B not have in it? The initial value plus the integral. Answer should be D. We don't put the 5 on the inside. The 5 is out front. It doesn't get integrated. That's where we started, plus the accumulated change. Four, 5, and 6. So for these, we could graph them and do the geometry area, but we're going to go a step up and look at them from the antiderivative standpoint. What is the antiderivative of 3 with respect to t? In other words, the derivative of what is 3? 3t. That's why the t is in here. So the antiderivative, the integral of this is 3t. We want to evaluate it from 10 to 4. So we plug in the upper bound. 3 times 10 is 30. Plug in the lower bound. 3 times 4 is 12. We subtract them and we get 18. If you were to graph this thing, and I'm only going to do it for this one, if you were to graph this, the graph of y equals 4 looks like this. It's a horizontal line. And from 4 to 10, it would give us that region. What is the area of this? Well, it's 6 for the base, 3 for the height. 6 times 3, there's the 18 from a geometry perspective. Okay, sticking with the calculus antiderivative, here's number 5. Evaluate this integral of 3t. The antiderivative of 3t, the derivative of what is 3t? So we're integrating, raising it a power. The t is going to be t squared. What number has to go in front of it then? 3/2. If you take the derivative of this, is that 3t? So you found the antiderivative. 4, 10. How do I know it went from t to t squared? Because I know my properties of derivatives. I'm thinking in the reverse. Running forward, not bad. Running backwards, a little bit harder. We can do it. Skating forward is hard for most of us. We have some experts in here that probably can skate backwards. The rest of us, maybe not so much. And integrating, we're all going to be able to integrate backwards. Some of us can do a little faster than others at the beginning, but we'll all get there. Now plug in 10. 3/2 times 10 squared minus 3/2 times 4 squared. I could put the 3/2 at the very end and factor it out. That would have been okay. And as far as answers go, boom. It's just algebra. It's just arithmetic. If you're really picky and you want to do that, I can evaluate like 10 squared 100 times this, 4 squared 16 times that. I believe it comes out to 126. But if it's non-calculator, you better believe I'm leaving my answer like that. Number 6. I'm going to slow down again. Now the integrand is 3t squared. Can you evaluate that one?
So wouldn't it just be like 3/2 t cubed? or no? One. I'm saying it's that. Whoever doubts me. I think it's not 3/2.
All right, t to the what power?
3/3.
3. But if I took the derivative of this, would that give me the 3t squared? Yeah. Right? The derivative of this is 3t squared. That's what I wanted. I want to know the derivative of what is 3t squared. There it is, from 10 to 4. So that's 10 cubed minus 4 cubed. There's my answer. Now, if I did my calculator and evaluated it, I believe that's 936. But the 10 cubed minus 4 cubed is good enough for us.